IEEE International Conference on Distributed Computing Systems. Abnormal message detection for CAN-based bus-based message transmission behaviors. University of Virginia, USA. Abstract: electronic control units and actuators in a modern vehicle communicate with each other through controller area network (CAN) bus to ensure driving safety. Current method assumes that the time interval or frequency of a normal message always keeps constant and detects abnormal messages by checking whether a message time interval or frequency changes. However, through real CAN bus dataset analysis, we find that time interval and frequency of the normal message may change greatly in different vehicle driving conditions, such as acceleration, deceleration, and drive mode shift, which can cause low detection accuracy of current method. To handle this problem, in this paper, we propose a message transmission behavior-based abnormal message detection system, METRDS, which detects abnormal messages in CAN bus-based message transmission behaviors, including frequency and message sequence. Through real dataset analysis, we find that message sequence usually does not change in different vehicle driving conditions, and also an abnormal message affects the frequency of itself and its subsequent messages. Accordingly, METRDS checks the message sequence dissimilarity to determine whether abnormal messages exist in a message sequence, and then checks each message's influence to itself and its subsequent messages to locate the abnormal messages in the sequence. We use a real dataset to test the abnormal messages detection performance of METRDS in comparison with state-of-the-art method. The experimental results show that METRDS improves the abnormal message detection accuracy of other methods by as much as 33.8%, and its memory and computation cost requirements are acceptable. Introduction: a modern vehicle usually contains hundreds of electronic units, ECU and actuators, first and second, which communicate with each other through controller area network (CAN), bus to form an in-vehicle network 3 and 4. The in-vehicle network monitors the subsystems in a vehicle, such as engine system, steering system, and rear seat entertainment system, to ensure vehicle driving safety and entertainment performance. For example, video play in a car, internet, 5th and 7th. Since CAN bus has several advantages, such as a less complex interface, high communication speed, and good fault tolerant 8 and 9, CAN bus has been widely used in various areas, including robots, ships, manufacturing industries, and vehicles. Though CAN bus provide an efficient and high-speed communication among ECUs and actuators 8 and 10 in communication process in the broadcast manner and has no message identification, which makes CAN bus easily to be attacked. 11 and 14. Under this situation, an adversary can inject a malicious message into the CAN bus through the vulnerable external interface. 15 and 17. For example, an adversary may inject a malicious message into the CAN bus of the vehicle via onboard diagnostics (OBD) port to adversely affect vehicle performance. These malicious messages possibly disable vehicle braking functions or stop vehicle engine. 18. Researchers have shown how to stop a Jeep Cherokee running on highway by remote launching a CAN bus attack. 19. Which triggered a recall of 1.4 million vehicles. Therefore, how to improve CAN bus security to ensure vehicle operation safety has become a challenge for robots, ships, manufacturing industries, and vehicles. By considering wide application of CAN bus in vehicles, here we only focus on secure problems of CAN bus in vehicles. Several methods 20 and 21 offer cryptographic messages identification on CAN bus messages to provide protection against the CAN bus message forwarding. However, the cryptographic message identification usually causes high message latency, which sacrifices message communication performance of CAN bus. Therefore, these methods are not suitable for the canvas in vehicle that requires real-time message transmission among ECUs and actuators. Other methods 1823 to 26 apply statistical based or machine learning based method. The statistical based method 18, 23, and 24 conduct a statistical analysis on the time interval or frequency of each type of canvas messages for abnormal message detection. A type K messages time interval in the time period because between this message and a previous type K message and in its frequency in the number of type K messages appearing during the past unit time period, for example 0.01 second. These methods determine that a type K message is abnormal if its time interval or frequency is in the normal statistical values range of time K message. However, vehicle driving conditions such as key on, key start, acceleration, deceleration, and driving mode shift usually varies during a driving process, which affect canvas messages, time interval, and frequency, and cause low detection accuracy of these methods. Machine learning based method 25th and 26th utilize machine learning technologies to capture underlying features, for example time interval and frequency of canvas messages, and apply these features to detect abnormal canvas message. However, there usually exist more than 100 different types of canvas messages in one vehicle, and abnormal messages can create a tremendous number of feature patterns, so the machine learning based method need a large amount of canvas message data for model training in advance, which limits their wide application in practice. Besides, both of these statistical based and machine learning based methods only focus on individual messages itself but ignore possible effect of abnormal messages on each subsequent nearby messages, which otherwise can be leveraged to further improve abnormal messages detection accuracy. Therefore, we need effective abnormal message detection technologies that can accurately detect abnormal messages in the canvas without the need of a large amount of training data for model training, and can consider the effects from varying vehicle driving conditions and nearby abnormal messages. To meet this need, we propose a message transmission behavior-based detection system, MetraDS. To the best of our knowledge, this is the first works to implement an abnormal message detection system that works without the need of a large amount of training data and consider the effects from vehicle driving conditions and driving abnormal messages to improve detection accuracy performance. The design of MetraDS faces two main challenges listed below. The first challenge is how to detect the existence of abnormal messages under varying vehicle driving conditions. In vehicle, each type of canvas messages are usually initiated with fixed time interval or frequency by design to ensure that the message can be efficiently communicated between ECUs and actuators. However, the time interval or frequency of a type of message changes greatly when a vehicle works at varying driving conditions. It is difficult to accurately detect abnormal messages if only the time interval or frequency is used as message transmission behavior features. We confirmed this by our real canvas dataset 27th analysis, and also found that in different vehicle driving conditions, a message sequence keeps almost constant. A type K message sequence is a series of messages from itself to each preceding type's case message. For example, for a series of messages ID present message types ID3, ID4, ID1, ID2, ID3, ID4, ID1, 2, 3, 2, 4. The message sequence of the eighth message ID2 is the ID3, ID4, ID1, ID2 based on this finding. We use message sequence as a feature to describe transmission behavior of messages, since this feature can more accurately describe a message transmission behavior without the influence from different vehicle driving conditions. In the In the above example, assume that the 10th message ID2 is abnormal and the other messages are normal. Then each message sequence changes from ID3, ID4, ID1, ID2 to ID3 to ID2 every time when CAN bus receiver receives a type K message. MetroDS checks the dissimilarity of this messages sequence with the previous few normal type K messages sequence, which were determined not including abnormal messages based on their Hamming distance. If the average dissimilarity is larger than threshold, MetroDS determines that this message sequence contains abnormal message. The second challenge is how to accurately detect abnormal message in a message sequence that is found including abnormal messages. When a CAN bus receives a message, it derives its message sequence and calculates its frequency or time interval. Through real CAN bus dataset analysis, we found that an abnormal message will increase its own frequency, i.e. decrease its time interval, and also reduce the frequencies, i.e. increase the time interval, of each subsequent messages in the same message sequence. Thus, we design metric called influence to reflect both of these influence, so that an abnormal message has much larger influence than that of a normal message in the same message sequence. By this way, MetroDS can accurately detect abnormal messages in a message sequence that is detected to contain abnormal messages. Our contributions are summarized below. We conduct a statistical analysis on real CAN bus messages underlying varying vehicle driving conditions. We find that they are under varying vehicle driving conditions. Time interval frequency of a message changes greatly, but each message sequence keeps almost constant. Therefore, time interval and frequency are not sufficiently effective, while relative message position is more effective in detecting abnormal messages. We also analyze the message sequence dissimilarities of normal messages and of abnormal messages, and find that the latter tends to be larger. Further, we analyze and notice influence from an abnormal message to sequence messages in the same message sequence in the interval and frequency. We propose a MetroDS to more accurately detect abnormal messages in CAN bus. To consider the effect on vehicle driving conditions and an abnormal message on each subsequent message, we first develop a message sequence dissimilarity measurement method to determine whether abnormal messages exist in a message sequence, and then we develop an influence power measurement method to calculate the influence from message to itself and to its subsequent message in message transmission behaviors to determine which messages in the message sequence are abnormal, based on CAN bus message dataset from different real vehicles. We conduct an experiment to compare MetroDS with state-of-the-art abnormal messages detection method. The experimental results show that MetroDS improved the abnormal messages detection accuracy of state-of-the-art method by as much as 33.8%, and its memory and computational cost requirements are acceptable. The rest of this paper is organized as follows. Section 2 presents our analysis result on real CAN bus message under varying driving conditions. We presented the details of MetroDS in Section 3 and evaluate its abnormal message detection performance in Section 3. Section 4 and Section 5 present the related research works on abnormal message detection. Finally, we conclude this paper with the remarks on the future works in the Section 6. Analysis CAN bus message transmission behavior. We conduct a statistical analysis on CAN bus message dataset collected from one real Kia vehicle under different vehicle driving conditions. 27. The dataset includes 369 268 normal messages, and then 244 0.041 abnormal messages indicated in the dataset, and 487 types of message. We group Canvas message in dataset based on message IDs so that each message group contains the same type of messages. In the message group result, there are total types different 487 messages group, and all messages each message group are ordered by their timestamp.